Welcome to this lecture on predicate logic, in which we will focus on quantification. So first, let's return to our flipper and dolphin example, in particular to the sentence S1 that we were stuck on in the previous lecture. Remember how the sentence all dolphins are mammals ended up being translated in predicate logic as D of x implies M of x. In other words, if x is a dolphin, then x is a mammal. The problem with that translation is that this expression of predicate logic is not a proposition, because it does not have a truth value until x is given a specific value. Since even in predicate logic we can only deal with propositions, we must do something to turn this expression into a proposition. And here are two possible ways to go about that. The first way is simply to assign a specific value to x. But there's a more interesting way to do that. In other words, one could also specify not a specific value for x necessarily, but a range of values over which x could range. And so that range of values, of course, would have to be a subset of the universe for x. So this is the approach that we're going to consider in this lecture. So this second approach is a more general approach than the first one. In fact, it's not hard to see that this first approach is really a special case of the second one if you consider that a specific value of x is nothing but a subset of the universe with only one value in it. Here what we're saying is that we allow x to take on more than one value. It can take on a value in any subset of the universe. So that sounds a little bit vague at this point, so let's make it concrete by using a specific example. In this particular case, we're going to use a new symbol shown here, which is an upside down A, and that symbol is read for all, and as a result this whole expression now is read as for all x, D of x implies M of x. And what that means is that now we're not stating that simply for an unspecified value of x, this proposition is true. What we're saying is it must be true for every single element in the universe. In other words, the subset of the universe that we're considering when we use this symbol is the whole universe. And by the way, this symbol here is called a quantifier, and this whole process of extending an expression like this one and turning it into a proposition by preceding it with a quantifier is called quantification. Now let me make two observations about quantification. First, what is quantified is a variable, and this variable must appear right after the quantifier symbol. In this case, the variable that's quantified is the x. So in other words, every quantifier must be followed by one and exactly one variable, the one it quantifies. Now, the second observation is that I indicated with red parentheses here the scope of the quantifier. So the scope of a quantifier is the part of the expression, in this case it happens to be the whole expression, that the quantifier is applicable to. So in this case, because the scope of the quantifier starts here and ends there, both of these occurrences of the variable x belong to the scope of the quantifier. In other words, before the quantifier was added, these two occurrences of x at unspecified values. That is not the case anymore because they are under or within the scope of the quantifier. Both this x and this x are specified, or their possible values are specified by the quantifier whose scope they belong to. So the significance of this second observation is that by adding the quantification, we turned something that was not a proposition into a proposition. In other words, this expression here is definitely a proposition now because the value of x is not unspecified anymore. So what that means is, before we added the quantification, it wasn't clear at all which value of x was intended when we said d of x implies m of x. And as a result, this expression was not a proposition. It didn't have a truth value. But now, with the presence of the for all x in front of the expression, we don't have a doubt anymore as to what value of x is implied. In fact, this expression, d of x implies m of x, is now claimed to be true for every single possible value of x in the universe of that variable. So this is a very strong statement, but there is no doubt whatsoever as to the value of x. Therefore, the resulting expression is a proposition. It's a quantified proposition, but it's a proposition nonetheless. So to conclude this example, we obtained a full-fledged proposition here that corresponds to the English sentence S1 from our previous argument. And to do that, we had to add the quantification for all x to correspond to the English word all in that sentence. And that's the only thing that was missing from the previous translation. Now, quantification is a very common phenomenon in English. There are many words besides all that denote quantification. So let's look at a few of these words. Besides all, you could have seen the word every. And by the way, every dolphin is a mammal is synonymous with all dolphins are mammals. But other quantifications are different. Like some dolphins are mammals, or most dolphins are mammals, or no dolphins are mammals. Those are completely different meanings, obviously. Another one is at least one dolphin is a mammal, or a few dolphins are mammals. And our last example will be many dolphins are mammals. So in conclusion, we see the need for taking care of quantification since it's a phenomenon that appears so often in English. And in this lecture, we are going to worry about two particular kinds of quantifications, namely the one denoted by all or every. That's the one we talked about on this slide, and we're going to get to again in the next one. And the second type of quantification we're going to focus on is this one, at least one. That will be for later in the lecture.